Hi, everyone. As you get ready to post some ideas and thoughts in the thread of discussion, um, I've got 3 prompts in there for you. And I'd like to talk to you a little bit about some of the things that are in the field book, but I wanted to start with some jokes from Huck. So this first joke I like. The physician, the lawyer, and the statistician were hunting, and the physician missed by a yard to the left, and the lawyer missed by a yard to the right. But the statistician's happy because they average out to be right in the middle. That means, the shot made it. And sometimes we do things like this, ridiculously statistical. Neither one got the deer, and the statistician didn't even try. So occasionally, and we talked about this in class with the article, occasionally statistics aren't the whole answer. We may want to use some common sense here and just talk about what's happening. There were 4 people who wrote into their forms that they were suicidal and yet didn't tell the doctor. I don't really need a statistical analysis of that. I can just stand back and say, wow, okay, interesting, fascinating, and maybe we need to take some action on this. Okay. And then here, this joke is funny too. So think about some of the different post hoc tests that we'll be talking about. Actually, Cronbach's not a post hoc test, but we have this Cronbach's alpha. You can think also of an alpha level, that we set usually at 0.05. That's for our hypothesis. Alpha is far better than omega. I don't know if you like Greek letters. Okay, and then Cohen, remember, is one of our effect sizes. He says to listen to your higher power. Okay, here's Tukey. And Tukey, if you notice, is Tukey HSD. Honestly, significant difference. And so here's Tukey, be honest. And Tukey really took issue with Fisher. And Fisher would have been a couple of generations ahead of Tukey. So I'm not sure they were alive practicing statistics at the same time, but Fisher supposedly felt like his LSD, his least significant difference, was the right way to do it. And Tukey came along and said, no, that's not even honest. And so Tukey named his honestly significant difference. And that's the joke here. And Fisher, of course, tried LSD, which is actually a psychotropic drug that's illegal in the United States. So just a joke. We actually am encouraging you not to use Fisher. His method of post hoc test has a bad reputation. And then Dunnett, control yourself, and that's because Dunnett always has a control group, which sometimes can be very useful. And then Spearman, keep your things in order. Spearman is one of those types of correlation. Maybe you'll remember from a couple weeks ago that rather than using the sums of squares, it's for data that does not conform to that nice normal curve. And so to do a Spearman correlation, we order all of our data. In the same way, to collect a median, we would order all of our data. So keep your things in order. Okay, well, that's Huck. He's funny. I also really appreciated this quote, and I'd like you to think about this. Hopefully, I'll emphasize this again and again. Down here at the bottom, a one-way ANOVA cannot make the study worthwhile. I can have perfect numbers, and I'm going to go through here and show you the numbers and where they come from. I can calculate them perfectly. I know that SPSS is calculating the numbers right. But if I started with a study in which I asked my kids to take the survey, or maybe the questions were loaded or leading, or maybe my data entry was really sloppy and I have about 5 or 6 errors in there, any of those things are problematic. And we can't just say, well, but I put numbers on it, so I have numbers, everything's fine. Sometimes in qualitative research, we really, really push for that credibility and trustworthiness. And we figure in quantitative research, it's all numbers, so it should be fine. And it's not always fine. There are things that can happen behind the scenes that destroy a study. So feel confident that even if the numbers aren't a lot of fun for you, you've got that grounding. You're all graduate students who've dealt with this before and will deal with this again. And you know what makes a good study, and it's much more, way beyond the numbers. All right. So when do we use ANOVA? This week we're going to start playing with ANOVA. Well, we've already done t-tests when we've compared two different means. Now we're using Anova because we have more than two means. And maybe it's because we have three groups. Like in this libido data set that we've practiced with, there were three groups. There was a control, there was a low Viagra group, and then there was a high Viagra group. But it can also be maybe in a t-test we can compare males to females, but now we need ANOVA because we want to compare males to females at the same time as we compare graduates to undergraduates, so that we can see if the male undergraduates might be different from the male graduates, who also might be different from the female undergraduates, who might be different from the female undergraduates. And so we move to ANOVA. Don't worry too much about the regression parts of Field's book. What he's doing is helping you to understand that ANOVA, regression, correlation, even logistic regression in some ways are related mathematically. And so, if anything else, the bottom line about this is it should give you confidence. If you do a study and you say, I don't know, should I use correlation or should I use regression? Which is the right test? Is it going to be awful if I use the wrong test? It's not, because you should get the same results. You should get the same results from ANOVA that you would get from a regression, that you would get from a correlation analysis. The only thing is, ANOVA is so much better suited when you have groups, right? So if I've got three groups, I want to use ANOVA. If I use regression, I have to create those dummy variables, and it's messy. But if I have, say, something like age, and I've measured it from age 18 to age 96, then I want to use regression, or I have to put those people in groups. Sometimes putting them in groups works, but maybe I'm not sure where I want those groups to be. Do I have youngish and oldish and tweeners? Maybe I just want to take their age straight up. This one was 26 and this one was 27. I can put those into regression much more easily than into ANOVA. Okay, so here's a great question. Why not just use lots of t-tests? So say I have 4 groups. Why not take them 2 at a time? Then I'd have to run 3 different tests. I'd compare, actually 4 different tests, right? 1 to 2, 1 to 3, 1 to 4, and then 2 to 3, 2 to 4, 6 tests. Sorry about that. I'd have to run that many tests and just see how it all worked out. And I could see when I compare those which are significantly different and which are not. But we have one problem here, and that problem comes from this idea of the family-wise error rate. Okay, so look at this right here. Here's 1 versus 2, 1 versus 3, 2 versus 3, okay? So I've got 3 tests here, and each of those tests has a type 1 error. I could be wrong 5% of the time, because you remember we went ahead and cut off our decision on the hypothesis at 0.05. So if it's less probable than 0.05, if it's 0.03 or 0.01, then we say to ourselves, okay, that is so unlikely, the probability is so low that I'm going to reject my hypothesis, okay? But now I'm doing it 3 times, 3 different times, and each of those times, it's possible I'm wrong. 1 time out of 20, which is 5 times out of 100, I'm going to be wrong. So on that first test, there's a 1 in 20 chance I'm wrong. On the second test, there's a 1 in 20 chance I'm wrong. On the third test, there's a 1 in 20 chance I'm wrong. If I ran 20 tests, one of those should be wrong, right? Because if there are 20 tests and 1 in 20 is wrong, one of those should be, by definition, wrong. And so what we do is we can calculate this family-wise error, and this is the formula, but you don't need to know this. For every test that we run, see that little n up there as the what we do is so for this example, sorry, I'm not saying this very well. For this example, we have 3 tests, okay? So n, which is the exponent here, would be 3. So we'd multiply 0.95, 1 times 0.95, 2, times 0.953. And each time we multiply by 0.95, this number gets a little bit smaller. I won't take the time to pull out my calculator, but 0.95 times 0.95 might be 0.92, and then times 0.95 again might be 0.89. So now my error is not just 1 minus 0.95. My error is not 0.05. Now my error has risen because I keep multiplying 0.95 times 0.95. So my family-wise error might be 1 minus 0.89 or 0.88, which is 0.12. So all of a sudden I've changed my alpha, even though I didn't really want to, I didn't really mean to. And that's why we do these post hoc tests, because when we run Anova, we're running an omnibus test, and we're just looking at the whole range of that variable. Is there a difference somewhere? We don't know where. We don't really care where. It's an omnibus test. And if it does come back significant that there is some difference, then we can go in and find out where that difference is. When we run Anova, we don't have that problem of family-wise errors. So we know that we are running one test with a 0.05 probability of rejecting our null, of accidentally rejecting the null if it's not supposed to be rejected. Okay, so this omnibus test does not change our alpha 0.05. As I talk to you about these things, feel free to pause and look at how Field explains it. Huck has some things explaining this. His explanation isn't quite as in-depth, but I love the way he talks about things. And in fact, Dr. Young calls him Sky. He's just the most personable, relatable statistician out there. So check both of the books if you need a little more sense of where this is coming from. What I wanted to show you really quickly was the math. This is the math that is going to come up in your output. And in fact, you've already done this, and I'll have you do it in more depth this week. But what we have is we have this model sum of squares. And that's the sum of squares that we can attribute to the fact that we have three different groups, and to the fact that we think that those three different groups vary from the overall mean, that they're different. Three groups that are actually different. And then what we do is we compare that to the amount of variability that's just there. In statistics, we often call it noise. Noise is just variability. It comes from maybe our personalities, maybe our approaches to life. In this case, in the libido, it comes from health and maybe stimulation, maybe even calorie intake for the day, all sorts of things that'll affect that we didn't measure. So they're kind of noise because they do make a difference, but we didn't measure them. Okay, so if we find out that the model tells us, can account for more variability than just all that noise that's out there, then we say we found a significant effect here. Our ANOVA is significant. And so look at this here. We have a total sums of squares. So what we do is for all of our data, we kind of ignore the groups, and we just calculate a mean. This is the mean of the entire data set. And then what we look at is, well, how much of that mean can be explained by the fact that there were three different groups. So the fact that we had a control group, a low Viagra, and a high Viagra. How much can that explain? And then how much can't be explained really by anything that we have. So it's just the noise. Okay, and we want this SSM, the sums of squares for our model, to be greater than SSR. And SSR, sums of squares residual, that is our noise. Field calls it the unexplained variance. And so you can see what happens here. This is kind of a fun a little chart. So these are our data right here. We've got a red group, a green group, and a blue group. And the nice thing is this is the Viagra data set, so hopefully you're a little bit familiar with it by now. And what Field does here is he shows, see this line down here, mean 1, that's the mean of the control group. Mean 2 right here is the mean of the low dose group, and mean 3 is the mean of the high dose group. And then this black line right here, the grand mean, that's just the mean of everything. We ignore the fact that these people were in groups, and we just take the mean of everything. Now visually you can see that the control group is below the grand mean. The low dose is below the grand mean, but it's pretty close, isn't it? And then the high dose is quite a bit above the grand mean. Now we're going to ask ourselves mathematically, is there a difference? And we do this by calculating the sums of squares. Sums of squares are pretty simple, but thank goodness we don't have to calculate them by hand. So here on our x-axis, we have our independent variables. That's the thing that maybe we assigned. That's the input, the thing that goes into the equation. And then over here on the y-axis, we have our dependent variable. That's the thing that we think depends on what we entered into the experiment or entered in as maybe demographics, right? So because the independent variables are on the x-axis, we measure along the y-axis for these sums of squares, because the y-axis is where we're looking for the difference. We're looking for that whatever we assigned on the x-axis to change the y-axis, the dependent variable. So say these straight lines, they go straight up. They don't go diagonally, straight up onto our grand mean. And we measure the difference between each of these measurements, each of these red dots, and the grand mean. We take that difference and we square it. And part of the reason we square it is for every red dot under the grand mean, it's going to be a negative number, right? Like this could be 1 minus 3.5. Well, that's a negative 2.5. So we'll go ahead and square that. So all of our numbers are positive. We add them together, and that is our sums of squared. So our sums of squared total comes from taking each one of those points and subtracting the grand mean. Then we divide that by the number of points minus 1. So it's very much like a standard deviation, and we get our sums of squared total. And this is actually the sums of squared total for that Viagra data set. You can go back and check it. Make sure SPSS got it right. Okay. The degrees of freedom are the number in our sample. In this case, there were 15 minus 1 because we just calculated one mean. It was the grand mean. Okay, so we have 14 degrees of freedom in this total. And the total comes up in the output. But this is not going to be as important as the next two. And in fact, we don't report anything from this. So be careful. Sometimes I get tempted to report the total in my degrees of freedom. What I really want to report is the sums of squares for the model divided by the sums of squares for the residuals, that unexplained variance. So the sums of squares for our model is pretty simple. We only have 3 calculations. We take each mean, because in our model we can include all the members of a group together and represent them by one mean. So here's the mean for control, here's the mean for low dose, and here's the mean for high dose. And we subtract the distance between that mean and the grand mean. We square those again. This is all that mathematical notation. Don't worry about it too much, but it's kind of cool. So we square each of those means. We add them, each of the difference between those means and the grand mean, we add them together, and we come up with this sum of squares for the model. Okay. We used 3 means to calculate that sums of squares for the model. We're going to subtract the one mean, the grand mean, which gives us 2 degrees of freedom. And this will be the first number that we report after the F. So we report that capital italicized F, and then in parentheses, or if you want, like the article we talked about in class, you can use a subscript. We would put the 2. Okay, stay tuned for what comes next. Now these are the sums of squares that we can't really account for. We can't account for them with the mean. We didn't measure things that might be causing some of this, and even if we could measure everything that caused this, there's still variability in life, right? We're all a little different. Every day is a little different. So in this case, we're subtracting the difference between each data point and its group mean, because even after we've put them into groups, there's some variability. We can't explain that. So this is the unexplained variance. The sums of squares, residual, that's what that little r is. And you can just write SSR, the r does not have to be a subscript. Okay, so this is each of the data points minus the mean for the group that they're in. Okay, and we end up here with this, the sum of squares for group 1 times the sum plus the sum of squares for group 2 plus the sum of squares for group 3. Okay, and we come up with this sum of squares residual, and this should be the same as your SPSS output too. Okay, so now what are the degrees of freedom for this one? This one's tough, and you can just grab this right off of SPSS. You don't have to figure it out yourself. This will be the second number after the F, parenthesis 2, comma. This next number is 12. So the reason it's 12 is because each group had 5 data points, and we used one data point from each group to calculate the mean for each group. Okay, so then Field just has us double check. The total sums of squares has to equal the sums of squares for the model and the sums of squares we can't explain. It makes sense. I mean, here's my total. This sum of squares here are the ones I'm trying to explain, the sums of squares for the model, and the sums of squares for the residual are the rest that I can't really explain. Okay, likewise the degrees of freedom, my total degrees of freedom should equal the degrees of freedom for my model plus the degrees of freedom for the other things that I can't really explain. Now, there's one little step that you see in SPSS, and it's because before we calculate the F, we need a mean squared error. So not just the sums of squared, but we need a mean, which means we divide each sums of squares by the degrees of freedom. So here's the mean for the model. Here's the mean for the residuals, or the ones we can't explain. Okay, now all of a sudden you can see there's quite a difference when we divide through by the degrees of freedom, 10 versus about 2. And sure enough, when we take the mean of the sums of squares for the model divided by the mean of the sums of squares for the residuals, we end up with that F, 5.12. And along with that, SPSS tells us the probability that we would find that given our null hypothesis. Okay, so here are some hypotheses that the researchers may have thought of. People who take Viagra will have a higher libido than those who don't. That the placebo is different from the low group and the high group. They might also think that people who take a high dose will have a greater libido than those taking a low dose. Those are all hypotheses that the researchers would have had coming into this experiment. And this is an experiment because Field randomly assigned people to these different groups and to these different doses. This is where we switch a little bit because in our research, we're not doing experiments. We're actually using our demographics. We haven't assigned those to just look for differences. And so Field moves forward and he uses planned comparisons. And planned comparisons are fantastic because in a planned comparison, you can increase the probability of having a significant result because you thought about this ahead of time before you even performed the experiment. Post hoc tests are great, and I see them all the time, but there's a little bit less of a probability that we'll actually get a significant result when we're using post hoc tests, and that's because we're coming in after and we're kind of looking. We think there are going to be differences, but we're not sure where, and so we're using a post hoc test after we've given our survey and looking for the results. And so in these post-hoc tests, we compare each mean against all the others. That would generally be a Tukey test. And it's a little bit hard to come up with things that are significant, and that's because we're kind of being punished for running so many tests at once, but that's okay. The post hoc tests completely control that family-wise error rate. The simplest post hoc test is just the Bonferroni method. They take the alpha and they divide it by the number of tests. So if you have 10 tests, alpha goes from 0.05 to 0.05 divided by 10. Now alpha is 0.005. So it's much harder to find a significant result. Here are some recommendations from Field. Notice his will be a little bit different from mine, which will be a little bit different from Huck's. SPSS has 18 types of post hoc tests, and there's not complete agreement on which are best. Field thinks the REGWD or the Tukey, which is one that I really trust. The Tukey is it's a strict test that if you find significant results with Tukey, you've done a good job. An even stricter test than Tukey is Bonferroni. That's a very well-respected test. With unequal sample sizes, I would still go with Tukey or Bonferroni, but Field suggests Gabriel's or Hochberg's, Games Howell, and we won't talk too much about this yet. The unequal variances means that we haven't satisfied the assumptions, that we need to approach our data a little differently. Stay tuned, this is coming up in a couple of weeks. Here's our post hoc test output, and I would encourage you to look at the practice assignments that I've given you. I'll show you in there which of the outputs you would use, and we've talked about the article in class about how those researchers reported that output, and we'll talk about ways you can do that. But basically, in a nutshell, that is Anova. It's fun, it's cool, there's so much you can do with it, and there's a lot of flexibility. Which actually is good. That gives you more power to make decisions for the research you're doing. Thanks for listening.